Welcome to the second part of this lecture, where we are going to be speaking about synthesis of amines. Now, the first part, we spoke about some properties. Now we're going to be speaking about synthesis. This should be a little bit shorter than the first part, where we will then be focusing on each of these syntheses in future lectures. So for now, the main aim is to have an idea of what we can do and how we can use them. The important aspect here is that at the end of the day, you have an idea of what you should or should not be doing when preparing an amine. So the first method is alkylation. You can either alkylate ammonia, a primary or a secondary amine. You can also actually alkylate a tertiary amine to prepare the quaternary salt, but we're going to be using quaternary salts as something on their own and not as part of amines. Now, here they have a big problem. How do you stop the reaction wherever you want? So let's say I want to produce methyl amine or methanamine. So I need to add one CH3Br to one ammonia. But the product that I'm making is more nucleophilic than the starting material. Therefore, it's going to react more than ammonia, so it will produce the dimethyl salt, the dimethyl product, which is then even more reactive and more nucleophilic than the monosubstituted, which will produce the trisubstituted. So in order to try and avoid this, to try and avoid over-alkylation, use excess amine or ammonia and add the halogenol alkane as a limiting reagent and purify after, for example, adding 20-30% in proportion. Okay? Now, this might take some time, but it's a good way how to try and avoid over-alkylation. Remember, probability will mean that the reaction will take place. The only difference is that if the probability is higher in the beginning, it starts to decrease when the substituted product will start increasing and your reactants will start to decrease. So in the beginning, you will only form one product, but then you will have competition. Okay? So this has to be a ratio where you are comfortable with the substituted products. You can also use nitrites. Now, this will give you one product only. But here, you will need to do a substitution reaction first, and you need to use cyanide. Me personally would try to avoid using cyanide because cyanide is highly dangerous, okay? It can kill a human with very small amounts, and it's not something that you should be using in the lab, okay? Especially at undergraduate level. But this would then give you your product, okay? And it is something that is gonna give you a pure one single compound after reduction, okay? So you need 2 steps, but again, the number of steps aren't the most important, okay? Because if we're gonna have one product at 95% yield, it's better than having, okay? It's better than having 3 products at a lower yield and a mixture. So the number of steps becomes slightly irrelevant, but the cyanide ion is still a problem. Okay? We can also use nitrations if you have benzene ring. So this is still an amine, but it's not normally an amine that you can produce using, it's not an amine that you can produce using normal non-aromatic chemistry, okay? Here you need to have an aromatic ring, and you are nitrating it using a nitrating agent. Nitrating agent normally would be the nitric acid and H2SO4 as discussed in the first chapter. Okay? Now, do remember that you can move from and to the nitro to the amine, okay? By either reducing it or oxidizing it. For reduction, I still prefer 10 NaHCl and refluxing, okay, to try and avoid using hydrogen. Hydrogen is not something I'm too comfortable using, as it's a gas and you need to have everything under specific conditions. I try to avoid using flammable gases, to be honest. It's true experiences of mine where I was on fire once, so I might be a little bit skeptical about using these items, but it wasn't hydrogen, in fact, it was another catalyst, not palladium carbon catalyst. But I try to avoid things that are too flammable. If they are unavoidable, then it's fine. You can use them, they're safe, but to minimize risk, 10 HCl works really well in this reaction. Then the best one would be the gabriel synthesis. And this solves the problem for over-alkylation. Now, here what you do is, you start with the dicarboxylic acid, okay? And you prepare, and you react it with amine, with ammonia, sorry, at 300 degrees Celsius. And this is a diamide. Apologies. Now, we have changed here from an amine to an amide, and the amide is already a little bit more acidic than amines everywhere. But the diamide would have a pKa of 8.3. This is an even stronger acid than an average ammonium salt. Okay? And in fact, you can use a very weak base, even potassium carbonate or sodium carbonate, to deprotonate. Okay? You can use a very weak base to deprotonate. Once you do this deprotonation, okay, then you've produced a relatively strong base, okay, which, apart from being a base, now you produce also a nucleophile. And this nucleophile can take place in a substitution reaction, okay? Normally it's gonna be an SN2 type of reaction, and it can displace a halogen and form a nitrogen carbon bond. When this nitrogen carbon bond is then hydrolyzed using sulfuric acid and water, you're gonna form a quaternary salt. And in order to remove the quaternary salt, you can then add a base. So here you have a reaction, you have a system of reactions where you're gonna start and finish with the same product. Now here you can say that the 1,2-benzene dicarboxylic acid, diphthalic acid, is not going to be the last step, but you can separate them before. You can separate them whenever you want, or else you can just add more acid and extract that and then that back to diphthalic acid. But this has to be pretty much 1:1 ratio. Okay, it's not a catalyst. It helps the reaction. It's self-generated, but it's not a catalyst. Okay, you can use it over and over and over again. At that point, maybe you can call it a catalyst, but even there, it's 1:1 ratio. Okay, but first you produce the diamide. Diamides are acidic. Even amides are slightly acidic, but diamides are purely acidic. Okay, that lone pair is gonna be distributed along the double bonds of the carbonyls. Okay, from one oxygen to the next. You have the ring as well. That is gonna be very, very acidic. As something like potassium carbonate can deprotonate the diamide to produce a salt, and this salt is nucleophilic. You can then use it in a substitution reaction to form nitrogen carbon bond. Hydrolysis of the amide or the diamide will produce the quaternary ammonium salt, which can then be reacted with a base to form the amine. The yield here is 73%. And why do I prefer this over the others? So, alkylation, you have a problem that you can have over-alkylation. It's a very simple reaction, you just mix two things together, but you can have over-alkylation. So, it's not going to be specific enough for most uses. Cyanide, it has a problem of using cyanidine. It's highly poisonous, it can kill you, and normally you want to try and be as safe as possible. On the other hand, sorry, apologies, the arene, the nitration, okay, you have a problem that you need an aromatic ring. So this solves all those problems. Another probably slightly easier reaction would be the reductive amination, okay, where you have nucleophilic addition followed by dehydration, where you form an amine, and then you can reduce this amine using lithium aluminum hydride, sodium borohydride, NaBH3CN. It doesn't matter. If you use something like NaBH3CN, this will only reduce the amine and not the aldehyde or ketone. Now, this reaction I have done in the past, and I found it to be very solvent dependent. In fact, you have to do this reaction normally advisable in ethanol, as it will activate the reducing agent. Or at least that's what I have found in the past. This is from my own experience. I can't really tell you it has to be 100%. I found a couple of papers on the topic, but I would recommend if you need to try it in the lab, try it because different chemicals, so maybe different carbonyls or different amines, might actually result in having some slightly different reactivities. Okay, and here it is easy to prepare secondary, tertiary, and to a certain extent even primary amines. Okay, and by finding the right carbonyl, finding the right amine, you can make whichever amine for your heart desires. Primary, it would have to be ammonia. I'm not entirely sure how easily this reaction would go with ammonia, but I believe it should work. But primary amines would definitely work. Okay, so you have to be a little bit cautious to see what happens. Yeah, it should work with ammonia, but let's say it's probably, again, you're using a gas, it's not the easiest chemical to handle. So if you have phenyl 2 propanone plus ammonia, you can get amphetamine. Remember, this intermediate is not going to be isolated, okay? You'll do the reaction in C2. You can either add everything together in the first place, or else you can add your chemicals one after the other. You add one chemical, you leave the reaction to take place, and then you add the second one. Both work. Okay. Normally, if the reagents are gonna make a difference, what you do is you add them in the first place, and then you just give it to the others. You just leave the reaction to go, and you have a one-pot synthesis. Now, this last reaction is an amazing reaction. Why? Because it's already a complex structure, and you are adding another pretty much tertiary group. And this happens without any problems with nearly 90% yield. Yield is everything. When we speak about chemistry, yield is everything. So you have to try and choose reactions that will work very well. Now, what's the difference? What's the problem between this reaction and the Gabriel synthesis? Okay, both are very good, but here you are not going to be using amine in the Gabriel synthesis. The amide, in fact, can sometimes be bought as an amide. So if you need to make it, to synthesize it, then, and you will normally not go, it all depends on which compounds you have in the beginning. I've always ever used the reductive aminations. Okay, I find it very useful. You can prepare pretty much anything, but you should know that there is another option. There is also formaldehyde in the secondary amine. Okay, this is similar to the reductive amination, where you are reacting a carbonyl with an amine, and this prepares the structure here, which is an important precursor in some drugs. Okay? Again, these items you should know. Maybe not the specific examples, okay? But if you need to make a secondary amine, you should know what you should be using. Okay? And I would say don't learn these specific examples, but do learn some examples, even if you have to invent them yourselves. Be creative. This is something where it's not going to be that difficult, especially since it's going to probably be an online exam, but you need to do your part. Then you can also have reduction of amides. So amides, we know how to make them using acyl chlorides and amines. Then you can reduce them to form the amine. Again, normally this seems to be a little bit too complex unless you already have the amide. So don't go through the amide if you don't have the amide ready and in your reaction mixture and you need to reduce it. If you can avoid using the amide, do so. Because to make the amide, you need to make an acyl chloride or an acetone hydride, which are normally not going to be the easiest and safest chemicals. There's going to be a couple of steps in itself. You might have to react with a carboxylic acid. Okay, if you have carboxylic acid, maybe you can prepare the amide, but always see what precursors do I have. Can I go to reductive amination? This would be the best way. Then, can I go to gabriel synthesis? Second option. If for those, the answer for those two it's both no, then look at amides. And you also have the Hofmann rearrangement, which is the removal of carbon dioxide, okay? And we'll be doing this instead of in the preparation of amines, rather in the reactions of amines or amides, okay? And this is a very important reaction. But we will be discussing this in our next lecture on Monday, okay? Hopefully Monday I'll be able to be back to an online lesson, okay, rather than a recorded lesson. So apologies for today, but the internet is a little bit dodgy, so I'd rather record the lesson and send it to you other than have you give you a lesson online and no one would be able to understand a thing. If you need anything, please don't hesitate to send me a message either on the Facebook group or via email, and I'll be able to help you. Okay? Have a nice day. Thank you for your attention. If you need anything, ask.